After that, you can start, right?
Sure.
Okay.
Sorry, I'm not quite.
You can start.
Okay, thank you. So hey everyone, this is Wen-Sen. You can call me Vincent. I'm from Qiskit Advocate Program. Thanks for having me here. And today I would like to share you with my personal journey and how I learned quantum information science. And hopefully this quick tutorial can provide some tips for your ongoing or future hackathon project. So before we start, I want to fill in a little bit about my background to you. I'm currently a research scientist in IBM Quantum, and my primary duties here are designing and simulating superconducting quantum hardware, including chips and packaging. And as an experimental person, I have nearly no knowledge to begin with in terms of coding with quantum computers. But I do know a little bit about quantum physics and how logic gate works in the classical computer. And I feel that we, or at least I am very fortunate to live in this generation to see the history when when the computer science was just born from maybe a handful of electronic device or processors into a full-fledged computer like these days. So if we look back into the history of classic computers, before the personal computers was born, there is a very intriguing period of time where these microprocessors are not yet used in the heavy lifting calculation task, but just some lightweight um, applications or even like creative applications, for example, like game consoles. And by coding to accomplish these particular tasks, we start to see the evolution of a classical computer and also the modern Homo sapien. Like from monkey, we become coders. And personally, I think this early development in the 1970s is exactly where we are now with these noisy intermediate scale quantum devices we have today. We do not exactly know how does this quantum computers look, how will the quantum computer look like in the future, maybe 20 or 50 years, just like we perhaps will never think about the possibility of to fit in a personal computer or laptop or game console into our pocket. But now everyone has a hand, like cell phone, right? Nearly everyone has a cell phone. But if we do not start learning quantum computer now, I think that they will never, perhaps never come. And that brings us, or at least bring me to the point where I start my quantum journey. So as a Qiskit advocate, I code quantum games during my free time and just for fun. And today I want to provide you two tips. Hopefully you will find useful in this event later. First one is idealization, or like how do I come up with some ideas of a particular quantum games. And the second one is the current implementations that at least that I am aware of, that how people do quantum games these days. Like, basically, there are some tools that we use to code quantum games, and I will after this the slides presentation, I plan to show you some um, coding. Just to quickly walk you through some idea how to realize the quantum physics inside a game development environment. So let's start with something that like overview. So as a quantum physics who is interested in promoting quantum education and also addictive to quantum games, I'm very interested in cultivating a community to generate quantum games. And from my experience, the best part of the game development is we learn through playing, and that is not just learning the quantum ideas, but also how to design our game. And by playing these games, uh, we we actually practice the ideas and we share the game, and we also play other games from other developers. So uh, a community hosting those developers are a key component for that. And these are my personal suggested bucket list that I think everyone should play if they're interested in quantum games. But that's just personal recommendations, and I can share the slides afterwards, um, so you can check it out. So first category, I put four categories here, but these are just like personal preferences. The first one is more like doing some physical experiments or simulations. And the typical example is this quantum game with photons. And since we have a little bit more time today, I can probably just like click it and share it. Like, like let you take a look. How does it look like? Um, okay, like this. So as you can see, this is basically a more like simulation game that shows you when the photon travels, how does the photon interact with the others or itself when they travel through the optical tables, right? So just basically you can see this and some polarization and some reflection, inflection, and so on and so forth. So this is one example that we have the one type of game that basically just do a simulation or experiment and then show it remotely to the players. So this is one type of thing that do the simulation. And second is we have some built-in game rules that is coded with quantum ideas. And the example can be very simple, like those text-based game. These two are, I remember, these two are just like Jupyter notebooks. If I click this again. This. So this CHS, like CHSH game, is basically, you can actually see it from, you can see the written instruction and the discussion from Wikipedia already. And the other one is, I think the other one should be a Jupyter notebook. Or, yeah, the other one is a Jupyter notebook that you can actually see the instruction. I think this is prepared by John Laman's group, and they use Qiskit code and try to walk you through the procedure of playing this game and also some very detailed instructions. This third one, this is actually a previous submission to one of the game jam that I participated, and I found it interesting. Although the um, the rule is actually very complicated for a beginner, and it took me a lot of time to understand at the beginning. So when I tried to play this game, but it was fun. Um, and the fourth one are quantum tic-tac-toes. There you have like can I think you need to do you need to download the app in your cell phone. It cannot be played online, but it's still but basically the idea is you want to form some kind of a line, but with quantum phase and also um, like with some probabilistic distribution and also quantum phase to win the condition. Right. So these are some simple ideas that show you the how do we code quantum games. Excuse me. Okay. Sorry, I had a bad cold these days, so my voice kind of like sour. Okay. So our next example is the Battleship example. All right, let's go back. So the Battleship with partial NOT gate. Basically, it's like a Battleship game, but you need to win the condition by hitting the enemy multiple times. And by multiple times, we mean when you flip the gate, they actually do the partial NOT gate. Means you need to flip it multiple times in terms of phase. For example, if your enemy is like if you're bigger ship in the Battleship game, you should end up with you need to shut it down for like 5 times, for example. And in that sense, we just divided the NOT gate, or like the flip of the quantum state with pi, right? And you divide it by 5, and then you flip it pi equal to phase with 1/5 of the pi, and then 2/5 of the pi, and then you hit it 5 times, and you defeat that battleship in particular. And let me quickly. I think it's also a yes, it's also a it's coded written by James Wooden, and it's the text-based Jupyter notebook. You can also play locally in your computer after download it. All right, so this then the last one is the quantum chess. That's I think it's by Google AI, and this is like classical chess, but just with some quantum rules, so such that when you travel, when you like the bishop and you will travel, then you have different probability to land at different points in the space in the chessboard. I mean, right? So I'm not sure if I. Okay. It takes a lot of time, so I probably don't have time to showcase that today. But anyway, these are some examples that where quantum inspired rules can be used to make your game more fun. And the third category is the puzzle solving ones that basically just put together some puzzles like so for example, the hollow quantums, you have some puzzles that need to be solved by okay. Yeah, it's probably need to. As far as I remember, this hollow quantum is also an app that is available on the cell phone as well. So you need to do download and installation. Basically, you need to do some. There are some quantum operations available, and just choose different operations with different order, and you can with the hope that you eventually match the pattern of the chesses. So that's like that's what I call it puzzle solving. Basically, these are some you want to match some kind of patterns. So this is another type of game. And last but not least, these are two Minecraft style games that I think developed by IBMers and also Google developers. That's available on. I think I probably won't be able to demonstrate here because it's Minecraft. Okay, I probably should not click on that. My computer is kind of stuck. All right. While okay, now it's back. I'll try not to click that again because this Minecraft things they will you will start this. But if you have Minecraft installed, then probably can get it. For some reason, my computer frozen at that point. The other examples are the fourth example that is the one that I personally focusing on is a real-time interaction. And the earliest and probably the most famous example is this Pong. It's basically ping pong game like in Atari, the generation of Atari. Right? That developed by and this Pong is developed by our Qiskit advocate fellow Junye Huang, and it's written in Pico 8, which is basically a Lua language. If you're familiar with that, so in this game, you probably cannot see my mouse after I go through here. But anyway, so you can see that there's supposed to be, you can see this at this column, right? There are different 8 different positions, and on the lower left here, there are 3 qubits where you can put different gates, X gate, Hadamard gate, and that's it. And by putting different gate here, for example, I put X gate, then I get 0, 1, 0, right? So I successfully defend myself. So this is an example that how by flipping the digit, that you can control your player's locations, and you can do some in-game real-time response. And to me, this is kind of interesting because as an engineer or with at least a researcher with a hardware background, we usually need to do a lot of real-time response in the, for example, simulation or daily works, is because the system we're tackling these days are huge with a lot of clusters, or you need to make a lot of decisions. And many of these engineering decisions, you need to make it in an efficient way, such that all of the instructions, such that you save your time, and all of this instruction becomes kind of our muscle memory. So that's where I started this thought. If I can do some in-game quantum, if I can try to force the user or the player to do some real-time in-game response with quantum ideas, then in that sense, I can try to train the users or the player to become the next generation quantum engineer. Let's put it this way. So if you are very familiar with, or like if you become very familiar with quantum gates, for example, then you will know that when people ask you what kind of quantum circuits that output a particular set of quantum states, then you can just tell them, okay, maybe you should put this and that, like put a Hadamard gate here, put a control NOT gate here, put X gate here to match the particular state you want. And the particular state distribution, and this is part of the part of the work where we want to build some quantum algorithms, right? This circuit language is at least this for the gate-based quantum computing model is the case, right? And that's what leads to my recent game development. It's called I think I renamed it to Kidding. So I had this game written recently, and it's also in Pico 8. So in this game, what I try to accomplish is, you can also see that there are still 8. Okay, there's still 8 bits here, from 000 up to 111. The red bar is 1, and white short bar is 0. And for example, this particular enemy requires us to put together a quantum circuit, the previous enemy, the previous example. Okay, let me just like, for example, now anyway, so that example requires us to shoot down an enemy that's falling at 110 and 101. And what circuit provides that? That supposed to be a Bell circuit, right? So you have a Bell circuit, but you flip the other digit here, and then you have a NOT gate here, right? So that shoots these two beams simultaneously to knock down the enemy. And you need to, as you can tell, you need to do it in a short amount of time. For example, you need to have a quick response in order to shoot down this particular need, no, like that. So and this speed can be tuned further, so you can drop further, and the user need to respond even faster to come up with some kind of quantum circuit to defeat the enemy. So this kind of in-plane, in-game real-time interaction is what I'm seeking for these days when I develop quantum games. So next up, let's take a quick example to showcase you how I came up with this idea from playing the Pong developed by Jin. So as I mentioned, actually I think I should pause here a little bit. Is there any questions or any response? So I wasn't like monitoring the chat or text box, or even if everybody's still with me. Okay, now I see the chat box. All right, then I'll just continue. Okay, so so in this coupon, they actually move the paddle. As I mentioned before, they move the they ask the user to move the paddle to a location represented by the state, which is given by the quantum circuit after measuring the circuit prepared by the users, like the quantum circuit here and the state representation here. And the reason why I like this game is because it's fun, and the real-time interaction actually requires user to create quantum circuits which match the given state distribution. And the user can potentially, but the drawback or the downside of this game is actually user can potentially win this game classically by just using the NOT gate to flip the digit and just match the state. And but it also requires the player to have, kind of precise alignment. By that I mean, if you try to play this game, you will know that like when you try to predict where the ball is there, like is dropping, then you have very hard time to align with which is this state or this state. But for example, these two states require very different flip. You need to do 3 flips to correct this state from this state, right? From 0, 0, 0, 1, 1 to 1, 0, 0. And that is not very that is not difficult in terms of quantum. It's difficult, but not difficult in terms of any quantum sense. So I was thinking, can it be more challenging in a quantum way? And that's how I come up with this idea. And after that, I noticed that I'll elaborate that more later on. So after you introduce some quantum idea, you actually need to also worry about the player not to exploit the quantum ideas to win the game. And secondly, can we try to make this game more difficult while game progress? And that is actually one advantage I think the quantum computation offer us to use it as a game idea, because quantum is difficult, and actually we can make it from less difficult to become more difficult to make the game more challenging. So I actually see this second bullet as a positive side of quantum game, that we probably don't need to worry too much, but we should think we should keep this in mind and involve it into our gameplay. Right? So the idea I came up with is I just let the enemy drop from 2 different sides. forcing the user need to introduce the idea of superposition and entanglement. So on the left hand side is still the old example where you just have one enemy following one particular column that you require us to use. For example, this three red block here represent X gate, the NOT gate. So you flip from 000 up to 111 and to shoot down the enemy. By the way, this is exactly the same game, or more or less the same game as the one I show you, the shooting game as I showed you before, but it's written in Pygame. And that is also the part of the thing that I'll address. What is the difference in terms of coding in Pygame and coding in Pico 8 in the later slides. But this slide here, I just showcase you the Pygame version, right, in Python and Qiskit. And the second column here shows that an example where where I try to invite the user to use superposition. In this example, I think it's 0, 1, 1 and 0, 1, 0. In that case, the rightmost qubit needs to be in the superposition state where we have 0 and 1 simultaneously. The middle qubit needs to be in the 1 state where we put the X gate, and the left one we just leave it do nothing, that will stay at 0. Right? So end up with 0, 1, 0 and 0, 1, 1, and you can have type two projection here that's supposed to shoot the beam later on. And furthermore, we can do ask a speaker to do the entanglement where for example, in this example, I think it's 110 and 001. It's a little bit more advanced than the Bell circuit. It's called GHZ circuit, where the three of the qubits are fully entangled with each other. And that's how to come up with this circuit in a short amount of time is also the challenge that I want the player to solve. So this is the entire game is what I came up with at the end. And basically this become a shooting game you just saw, where the pedal here are just representing the lasers, right? So next, what is called, okay, yeah. So after the ideas are more or less settled down, there are still likely, like I mentioned before, there are likely more bugs or fine-tune process that need to come up, that need to overcome. But like I said before, the best part of the game development is actually we learn through playing. So because playing is fun, and when after you coding, you see some progress, and you see some final product that you had, and you can play and fix it and make it better, right? So I see this as a positive thing. The first thing that comes to my mind is how fast animation drops, and the current game that I put into in the game I show, I think is optimized. It cannot be faster. If it's faster, it's very difficult to play with. But I also set it into increment level, like when you play longer time, like when you hit down more enemy, it become increasingly difficult, it become faster. And then secondly, I noticed that user can actually exploit Hadamard gate. By that I mean, because this is basically a shooting game, right? So ideally, the user can just put 3 Hadamard gates here, here, and here. And in that sense, the computer should just shoot 8 lasers at all states, right? So how do we prevent that in a logical sense or in a quantum sense? So the solution I came up is actually I use the quantum measurements just to do this. So in the QC code, I set the measurement shot to be 8. And then I only allow the pedal to show up when after I measure the quantum circuit that user provided. When the state count is greater than 2, I will do the laser. such that when the circuit with full superposition, it will give you an unpredictable state matching this criteria. So that's way how I try to get around with this exploit that people might use, the player might use. Okay. So hopefully now you're kind of aware of how the what are quantum games and how how we do how we find some ideas to create some quantum games. And next up, let me try to fill in a little bit more detail in terms of the current implementation of quantum game development environment. So to begin with, what we want to see in the quantum games are usually the game should be engaging and appealing, and maybe has some built-in competitive elements. Maybe like the one I mentioned before, it should have some increasing level differences. It should be challenging, and maybe some high scoreboard and PvP player versus player mechanism, and so on and so forth. And last but not least, probably the most important one, in fact, is it should be scientifically correct. For example, we need to explain to the detail to the player how this game was developed and why it is quantum mechanically correct, or in terms of information science, why it is kind of correct. And all of this should be formulated and serve as a guidance. So these two are the games that I'm currently working on as well, and that's I try to create some. I still try to use the circuit composer model as an input to create different in-game features. Okay, so now let's get started with the potential platform to code the quantum games. So as far as I understand, there are 5 mainstream that people are using that to code quantum games. The first one is perhaps most of the physicists like us knew, is the Python environment, which is basically Qiskit plus Pygame. The issue of this approach is the game build, like when you try to share your game eventually with someone does not use Python, is that when you try to share that file, you need to do some action, we call it game build. You build it into an executable file. And after you build a game, the executable file for this approach is usually over a few hundred megabytes. And I don't think anyone these days will play a small game with 100 megabytes and just waiting for the download. The reason behind this is because Qiskit actually involves a lot of visualization tool, including matplotlib. And during the building process, if you did not carefully remove those unused package, then the final build will usually over a few hundred megabytes. I think the standard one is 270 megabytes without any instruction in Pygame. So this become a big issue. And as a result, I tried to look into other solutions, and I found these 4 other alternatives over this year. And the second alternative is there are some developers have their own JavaScript quantum simulators, and so as a result, they can write the Java games with a built-in quantum simulator in JavaScript. Sorry, and the third option is the one that I'm currently working on with, is the MicroQSC in the native game development engine. For example, Pico 8 or TIC80, actually, if you prefer open source version and free version. And both are in LUA language, and this LUA language is easy to work with, although we do need to learn something new that is not familiar for us. at least I found this is relatively easy to learn with, and it's easy to draw and also put some sound effect as well in the Pico 8. So MicroQSC code basically is a piece of you can think it as a built-in quantum simulator that written in LUA, right? And it is prepared by James Woodens. I I think I have updated this slide for this page that I link everything here, and I can share it later on. I'll update this slide and share it later on as well. And fourth alternative is we still use Python, but we combine the power of the professional game engine, for example, Unity or Godot. In that sense, we need to use Python Flask to set up a server, serve as a server, just to interface between the result from Qiskit simulation and Unity game engine, the user interface, and that will give us a nice and beautiful view that's done by professional game development software packages, right? And last but not least is this new recent, I think it's this past years, the one of the Qiskit developers proposed is the Qiskit, and this Qiskit actually allows the user to code, to do Python coding inside Unity. So as far as I understand, in Unity you need to do C# programming, but this Qiskit is actually some, I would say, the Unity package manager can do it. You can install this Qiskit inside Unity such that you can just do Python coding inside. And I personally am trying this to see if I can just put my previous game written in Pygame into Unity after I connect the user interface, fix the user interface. If that works, then it becomes a very strong candidate for future development, for future game developer as well. So I think I go through more or less the pros and cons, but in previous slide. But I'll just the following 5 slides are just quick pros and cons that I think of, right? So just to walk you through again. So Qiskit Pygame, the process is a native Python environment which is physics friendly, and we can even explore more possibility like pause module that I was previously thinking with. The problem is it's difficult to distribute your game, right? Okay, and the second option is built-in quantum simulators with Java, and it's easy to distribute and it's flexible in file formats. The problem is there are actually not many open source public Java codes that do quantum simulations, as far as I understand. And as a result, we are expecting limited support resources. And third, the MicroQSC code is actually nice in terms of it's easy to distribute because, for example, in Pico 8, I can just write a code and build a HTML file and then send it to the web page that people just can play and give me feedback. And you have great design experience. And MicroQSC code is just like Qiskit code and it's physics friendly. The problem is Pico 8 is problem of Pico 8 is not open source, but for TIC 80 is free and open sourced. So consider TIC 80 later on if you want to keep working on this approach. And the fourth one, Qiskit Python Flask, it's easy to distribute, but the issue is the setup of Flask is not very physics friendly. And that leads to the last is the Qiskit and Unity that solve the difficulty for physics and also combine the power of Unity. But I haven't really tried it, so I'm not sure what it might give us in terms of troubles, but hopefully not. So in the last slide, I would like to invite those who are interested or considering in creating quantum games to think about who we are or who we want to be in the future. such that you can likely save more time if you choose the right path to begin with. So if you are pure quantum physicist like me or like most of us, I would highly suggest that you started with Qiskit and the Pygame for your very own first game. Right? And since that you are likely to code this game in a short amount of time without learning too many new stuff, like for example in your hackathon you probably don't have enough time, and you are uh, um, and later on you can pick different paths. Like if you like want to be a game designer in the future and you want a more beautiful game, you're focusing on game development. You can draw some good pictures and stuff like that in Unity, in Qiskit, um, and so on and so forth. Then I would suggest you check out the MicroQSC and Qiskit approach. But if you are more like a software engineer, your career goal is more like becoming a software engineer, then you can definitely go to the Flask and JavaScript alternatives, such that you can keep working on quantum computation in the future with those tools. Right? So I think that's most of the part of my talk, and I will try to do a quick demo afterwards. But what I mean, is everyone tired, or should I just like continue? What do you say?
Yeah, you can continue, Vincent.
Continue. Okay, cool. Then I will continue. So I'm sorry I have multiple screens, so sometimes I didn't look at the camera because I was working on different screens. Um, all right. This is like I mentioned, this is Pico 8, but I still I didn't share my screen. Sorry. Let me see what's the best way of doing this. Yeah, Pico 8 is relatively low resolutions. So can you let me know if you can see the entire Pico 8 screen, or just like the word is too small? It's difficult to see.
Yeah, it's perfect.
It's perfect. Okay, good, great. So this is Pico 8, and here you, unfortunately, I don't think you can see my. Oh yeah, you can see my cursor here. All right. So like I mentioned, this is Pico 8, but you can also go with TIC 80. And just quickly text it here. But this is another. Just by the way, I am not affiliated with either company, so I just want to provide some information for you that you might find useful. 80 is free, and Pico is not free, but Pico 8 has greater community, uh, uh, either developer or players alike. So you actually find more positive feedbacks from there. TIC-80 does not have a lot of community, as far as I'm aware of. So, but anyway, both supports Lua language, and in the game, you have different options here that allows you to do different things. This is where you do the coding. This is where you draw some pictures. By picture, I mean characters. So, for example, if I draw some pictures, characters, right? And like that. And then here you have some sound. Oh, but I'm not sure how to share my computer sound in Google Hangout. But so I'll probably skip the sound because you probably won't be able to hear it anyway. And what then in Pico 8, sorry, the coding started like this. So you have a function in it, do the initialization, and what I try to walk you through is a quick demo on how to use maybe like Qiskit code, or maybe like use I will start with some quick walkthrough about how do we do some in-game control, and then Qiskit code, MicroQSC code in specific. And then I will just quickly showcase the game that I'm recently developed with, just to give you some idea, or like try to give you some inspiration, hopefully, that you can be useful later on, right? So in Pico 8, the coding structures like start like init, update, and then I think it's draw. And the idea of any, I think most game development is after initialization, you will have infinite loops of update and draw. And each infinite loop represents one frame. And we have, for example, when you hear a game is 60 FPS, that means it's 60 frames per second. So within each second, the frame or update is 60 times. And so it's like you have, when you try to move the character to the left or to the right, for example, to the right. So the character moved one frame by one frame by one frame, a little bit, a little bit, a little bit. And after 60 frames, which is 1 second, it complete or it finish its action, for example. So as a result, when I do, for example, in the update, if I do some print, and I print some I just do this and then run the code, you see it's keep printing. It's just keep printing, printing, printing. However, if I do a draw here, if I clear the screen, you'll see nothing. Because after it do hello world, you just clear out. So as a result, that's what the first suggestion I'll provide to anyone that's from Python to game development, the world of game development, is you need to think about what is going on in your when you're doing debug. It's not just like you just try to do print. That's what I do. Like when I do debug, I just see where the code stop. But this print usually doesn't work because you won't see the computer print anything, because the frame is updated in every second, and sometimes you just like wash it away. So you need to choose this print, or like do the debug in a more careful at a more careful place if you're using this features as a debug tool. All right, so in Pico 8, there's let me start real quick with this. Maybe we have, let's try to do a Pong game. Let me try to do a Pong game. That's like just like Junye did, right? But probably not a quantum version, just a simple version. So I have a, let me start an object called ball, or a table. Actually, it's a table now. And yet ball.x and ball.y.
And get this job done.
Set a pixel on the screen at ball.x, ball.y. Maybe color 9. I do the clean screen afterwards. You see there's a dot in the middle of the screen, right? So what happened here is I just initiate a ball at a particular location. And in Pico 8, the development, you can see that it's very grainy. That means you have 128 on the X and 128 on the Y pixels. And in the middle is 64. And that's why when I put 64, I get, you'll see what I mean by this. 64, I get a middle. So if I 32, I get upper left corner. pixel. Okay? So for a ping pong game, then we have the ball ready, and let's get the ball rolling. Okay? Maybe 1 pixel at a time. 1 pixel and Y. And I want to make Vx and maybe just like that. Oh no, it should be X. Right? Velocity add the Vx, and since time is since it's updated every second, so it gives us an idea. So this is basically it's a v times t equal to x. So see the ball is going away, right? So this is an example where I think game is actually helpful in terms of learning, because in this example you just learn kinetics, like the classical mechanics through your game, and you can just change the parameters, like you make it faster, slower, and so on and so forth. So I think I won't bore you with all the details in terms of how I code, but I'll just open up I just copy paste my example code. And then you see how it works later on. So this is the example code that I came up with later on. So a ball and X, Y, right? And also I have some reset. By reset, let me just run the game real quick. So you see, I have X and Y for the other player, and up and down for the other player. So you can see that this is a classical Pong game. And it's relatively simple, which means I only use 85 lines to finish this code. And they're nothing fancy, just basically just it's basically, like I say, it's a mechanical simulation games that give you the how do you call it, this elastic collision. By that I mean when you hit some boundary, you had the velocity times equal to -1. You have velocity times -1, and you just change the direction. So basically, it's a elastic collision condition. And of course, if you go to the other side, you need to decide it's +1 or -1 in terms of the scores. Right? But that's it. That's pretty much it. Oh, and the other thing is we need some functions like buttons detections from users, but this can be easily found on the Pico 8 community or Pico 8 documentation. So I won't spend too much time on that. So this finished the part of the quick game introductions, developed introduction for a classical game that we were talking about. Now let's take a look about some. Maybe I should pause here. Is there any questions? While I'm loading. Oh, okay. No. Not sure. Let's see. Code is quantum. This perhaps not quantum, but so this one, this is not Pong game anymore. This is the ideal I try to realize, and I actually use the MicroQSC code that I think is a good example to quickly walk you through how to use Qiskit code or quantum ideas in your game, right? So, so hopefully now you're already familiar with these three functions, which is init, update, and draw in the Pico A system. That it's not very important in terms of quantum games, but it's important for game mechanisms that you need to know. But I split these three functions into three tabs because now game is getting increasingly longer. The fourth tab, which is 3, this is the entire MicroQSC code, and the fourth is some function that I wrote by myself, just to better interface the MicroQSC code to my own game. Okay, so the MicroQSC code, as you can see, is a piece of 285 lines code that do quantum simulations. That's written by James Wooden and his colleague. So you can actually it allows us to do the typical quantum operations like we did in Qiskit, and the language is very similar. So you have QC, define the QC, and then QC.x.h.cx, for example, and then you do you put in the a qubit number as a register, and then you do a QC.measure, for example, to get the result for basic quantum operations. So with that, I came up with some, maybe I'll just run the game and then show you what this thing does. So this thing, whenever I hit X, it generates a, let me do this. You can see from this, I'm not sure if the frame rate is supporting, but hopefully you can kind of tell that there are actually 8 positions on the screen that randomly pop up. That whenever I hit X, there are actually 8. The characters are showing up at 8 different locations, but sometimes they're showing 1, sometimes showing 2, right? And then whenever there are 2 characters, after a while they will collapse into 1 characters. Right? This is the thing that we're trying to realize in the game, that we can probably use it. But how do I do that? Basically, we need a quantum circuits, right? And then we need some kind of randomness. So the way I do it is in the update. I think this is where most of the code goes, quantum code goes. In the update, when user press button X, basically what it did is it create a quantum circuit and it set the quantum register with a certain number, where I use 3 qubits in this case, so such that I generate 2 to the 3, so it's like 8 possible positions, and I just simply superposition all the states, so I can do the I pick up random states among them after the measurement. So here, if you're familiar with Qiskit, then you kind of quickly recognize this thing. It's really like just a simple Qiskit code for a simple circuit with 3 qubits. Okay, and after I do this is just like the I think previously called job.run in Qiskit language. But now in Python, in the MicroQSC, it's called simulate. But anyway, it gives you some results, and I reinterpreted it into my own the numbers that I can use in my game, and I just show the character at the whenever we have detection on the either state out of the 8. Yeah, so and that's pretty much it. So you can see that in the init I have some initialization about characters and also location, and the draw I just basically just in each character I check if it should show up or it should not show up, right? And I think I commit like 1.5 hours today, but uh, but since I got a serious cold, I don't think my voice can support further a project for that. So we probably need to end earlier today, and that's kind of the end of my talk today. So do we want to have some quick? But I'm happy to have some um, Q&A afterwards if anyone is interested in. I will stay here to whenever you want to end. I'm all good.
Vincent, you had a question in the chat.
Oh,
Do you think quantum games
yeah.
should be used as an interactive learning tool to teach the principles of quantum
Oh, yeah.
mechanics in a basic level?
Yes. Thank you, sorry, Adari. Sorry, my pronunciation sucks, but yes, that's definitely the reason why I am into this field to start the quantum computing, because I like games, and I think game exists as an educational tool for many from many other examples, like that Microsoft had this flight simulators. That's basically it's a real time like flighting, like just let you get a feeling about how to pilot, to do the flight, to fly a plane, right? And there are many other examples. For example, there's this protein folding game that you can actually help the computer or like help the biology engineers to understand how the protein fold by analyzing, do some like online gameplay, like to make the computer basically make the computer learn more, do when they try to do the machine learning, right? So that is definitely an important part. But on the other side, though, I, quantum computation, I don't think quantum computation has shown any advantage in terms of creating games. As a result, most of the game company, they probably wouldn't care less about quantum computation or like how to invite this game into quantum computation. And that's the most important reason why these days we're only seeing indie game developers or like independent game developers in this field. And that is also why I summarized all of these possible platform that do the quantum computations or like do quantum computer games, because most of us are just alone, and we need a community to do that. Uh, we cannot rely on a big company because quantum computation is not that useful. It won't make you a more beautiful game or more like, but it will give you some like fun and your fun time at when or like give our kid or give ourselves some like knowledge or just to alternative to learn and to play, right? So that's definitely an important feature.
Thanks for the answer, Vincent. Are you continuing with the demo or?
No,
Okay.
not much. Thank you. Sorry, I'm having a real I'm having a real problem with my throat today, so I cannot talk more. But I can like try to share my thoughts if there's more questions. But if not, then we can. I'm very happy to end here. It's my honor and pleasure to be with you today. Thank you.
Yeah, well, we had a Discord. I don't add it because
Oh,
almost the server is in Spanish, but if you don't have any problem, I can
yeah,
add it.
sure. I can join and then you can ping me. But do you have kind of translation tool in your Discord? Or if
No.
not, I whenever I get pinned, I'll just ask, can you can you elaborate in English?
Okay. Well,
I'm happy to join and then provide my like 2 cents if you find it useful. But mostly I code in Python and Lua. I'm not very familiar with the rest of the code, but I can try my best to get some resource. Yeah.
Okay, thank you, Vincent. So, if anyone has any question for Vincent or after the meeting or you rewatch this workshop, you can pin in the Discord with a mentor, a robot mentor, and only refer it with the Vincent name. He knows, well, if you can write it in English, it could be better. If no, we can try translating for him. So don't worry in that part. And he can answer in the what moment you have. It could be in the hackathon or in the workshop time. The hackathon is in 23 to 27. So you had another question, I think no. So thank you again, Vincent, for your workshop. It's
Thank you.
always a pleasure listen your presentations and video
Oh,
games.
that's a great praise to me. Thank you, Alberto. All right.
Thank you, Vincent.
Take care, everybody.
So,
See you
bye.
around.